Hello, my name is Nathan Patrick Helton. I will be presenting on behalf of the Orchid team today, which also includes Oleg and Patrick Moss. Today I'll be talking about our results thus far in the semester. Just a topical outline for what I'm going to be talking about today. I'm going to give a quick overall objective of our experiments. I'm going to talk about the two systems which we've been discussing, the different methods we use to analyze them, and some conclusions based on those two different methods. Overall objective of the experiments that we've done is to observe and analyze a given control system in order to obtain system parameters, actually two given control systems. Parameters which we are interested in include dead time, the time constant, the system gain, and ultimate controller gain. The first system was we dubbed the duct cooling system. It involves a series of ductwork, which is made out of metal, which is heated by a series of two heaters, and is cooled by an air pump, which flows through the ductwork and out. And there are also some dampers at the end, which control how the air blows out. Our damper and heater settings were the same throughout, so that doesn't really affect our system per se. What's really more of interest here is the control system that defines the system, And so here we have a temperature element which is connected to the ductwork, which tells you how hot the duct is, and that's connected to a temperature transfer unit, which relays to a temperature control unit, which controls the air pump, which cools the thing. Something interesting about this system is the higher you turn up the power, the harder it blows, and the lower the temperature goes. So our control variable actually decreases with increased input. And so now I'm going to begin the discussion of the different things we did to analyze this system. First thing we did to analyze the system, something called SSOC method. What is the SSOC method and why do we use it? Basically, the SSOC is standard state operating curve. What we did is we took the system, we gave it a constant input, and we waited until the output reached another constant. And so this picture here shows the constant input in purple, straight horizontal line, and then the output, which is varying and eventually tries to reach a constant output. In all actuality, it wouldn't be constant because that would take an infinite amount of time, but it's close enough and we stop there. And what you do is, or what we did, was we ran a bunch of different experiments with different inputs in order to judge the different outputs. And the results we got from this are outlined here. We found that basically the temperature change is about negative 0.4 times the input percent. So temperature in degrees Celsius. And then something else that we did to analyze the system is called the step response. Basically, we get the system to steady state again, and then we suddenly change the input and wait till it gets to another steady state. It's kind of backwards compared to some of the systems other people are using because it's actually going down as we step up. The way that we get the parameters from the step response involves, well, one of the parameters would be tau. And tau is found by going, well, let me just explain a bit. This first horizontal line is the original steady state point, and this last horizontal black line in bold is the final steady state point. Once you've gone 63.2% of the way to the final point, the time it takes to do that after the system is changed is called the time constant. And then the system gain, which actually should be negative, it's a typo, sorry, and looks at the output over the change in output over the change in input. And then you can find what is called the dead time. It's a measure of how long it takes the system to react, kind of, judged by looking at this line here and trying to find the inflection point and then plotting a tangent, or putting a tangent line to that inflection point and seeing where it intersects with that original constant input. And that was a little bit difficult to do with our system, and I'll discuss that further in a bit. But just to summarize some of our step response parameters that we got. Gain for down steps and gain for up steps here. It's about an average of 0.1 for both overall. And then you have the dead time for the down steps and the dead time for the up steps. Dead time tend to be higher for the down steps for reasons that I'm not going to postulate. But overall, they're almost equal. And we also have the time constant for the down steps and up steps, as I've discussed before. And then we moved on to another way to try to find the parameters for the system, which is called FOPDT modeling. What is FOPDT modeling? It's first order plus dead time modeling, and it's a first order model based on a linear system that tries to emulate our system, and we manipulate the model's parameters until they seem to match our system, and then we assume that those parameters are relatively close to our system's parameters. And this graph shows one of our models. You can see the model, input in green very closely matches the experiment's input, and the model output very closely matches the experimental output. And some results that we got from the FOPDT modeling, the parameters that we got. And this also shows it compares the FOPDT parameters to the step parameters. You have your dead time, your time constant, and your gain here, and some associated uncertainties. Not really all that interesting. And then we move on to an alternate method, which involves numerical integration. And this method is actually loosely based off of the step response. And I was the alternate for my group, so this is the method that I did instead of the FOPDT method. And in this method, you look at your step response, and you have the first steady state and the second steady state defined by these horizontal lines. And then you have your changing output defined by this curve. And the area above is dubbed area 1, and then you use that area 1 through this relationship to find L plus T. Then you use L plus T to find, or area 0, excuse me. And then you use L plus T to find area 1, which is the area under the curve. And that all sounds nice and dandy, but why is this useful? Why did we do this? Why did we take the time to look at all of our data and try to do numerical integration on it instead of just doing the step response as we did before while looking at it? And for our system in particular, it was quite useful since, going back to the step response, it's hard to find the dead time for our step response. You have to plot a tangent line to an inflection point. What's an inflection point? What's a tangent line? And so by doing the numerical integration thing, we can circumvent that and find dead time another way that may or may not be more accurate, but hopefully at least has less human error. And so this is my result from the numerical integration. This is not Dr. Henry's plot, this is mine. It just looks a lot like his on purpose. And as I've discussed before, my step response is kind of backwards, so my A1's on top and my A0's on bottom. And that's my output line. This is the initial steady state. This is the final steady state. And now I'm going to discuss all the parameters that we've gotten from, including numerical integration method, the FOPDT method, and the step response. So this is all been concluded for the first system, which was duct cooling. And so here you have our system gain for the 3 different regions that we observed of the system, the lower, the middle, and the upper regions, averaging about 1 overall, 1 degree Celsius per percent. And this is dead time, the lower, middle, and upper regions, averaging about 0.5-ish to 0.05-ish. And these are time constants for the system in the 3 different regions for the duct cooling. And now I'm going to move on to the second system, which is absorber airflow. All the chemmies in this room know more than they would ever need to know about absorber airflow. They have been lectured on it completely. But for everyone else, as I'm a chemie and I'm in this system, I will try to explain it to you. So let's say you have a nasty gas, or a gas that's an output of some kind of reactor that has something nasty in it. And that nasty thing just happens to dissolve into water or some other fluid that you have on hand. So how do you get rid of that? Well, you use an absorber airflow system. What you do is you take your nasty gas and you push it up through this pipe. And then you take your water or other liquid in which it dissolves and you put it down and you let the water flow down as the gas flows up. And this pipe is filled with stuff. It's filled with packing. And this packing is designed to block the flow of the water and move it around to increase the area of reaction between the gas and the water, so that you can get the maximum amount of absorption of your nasty gas into your water. And that's all fine and dandy. Just thought I'd talk about that. But that's not really what we're worried about. What we're worried about is control system associated with it. More specifically, this valve, which comes from a pressurized air supply through this valve into the absorption column, as I talked about before, and this represents the fluid that will be flowing down. That would be absorbing your nasty gas, but we're not actually using a nasty gas, we're just using air. And this valve is controlled with a flow recording controller, and when the flow is sensed by this flow element, which is transferred by this flow transfer thing to the flow recording controller, which controls the valve, and that's our control system for the second half of our experiments. Alright, so what did we do to try to define the parameters for this absorber air column? Well, one of the things we did was the frequency response. This is just an example frequency response. You put an input, a sinusoidal input in, and you get a sinusoidal input out, and you shake it all about. And just briefly going over some of the results that we got from doing a frequency response that I didn't get, but my teammates got. This shows our actual phase angle versus frequency Bode plot. Our actual experimental data is plotted in green below the purple with the overlying model. Relatively good agreement. Like before, if you make the model match the data, the model parameters should be relatively close to your experimental parameters. Here's another Bode plot showing experimental data and also model data. And I'm going to hold off on the results of all this and put it at the very end because I'm almost there anyway. And I'm going to talk about the alternate method that I did personally, which was the relay response. And so what you do with the relay response is you have an input and your system gets an output that eventually crosses some kind of set point. And once it crosses that set point, your controller decides it's going to change to a different one until it kind of curves back down and then it crosses again. Every time it crosses the set point, the input changes, fluctuates back and forth, kind of like a relay. And you get some kind of sinusoidal output looking thing. And what do you do with this? How do you get parameters from this? Well, it's not pleasant. So you look at the different curves that you get, and you try to find different parameters based on those curves. One of the parameters based on your various curves is the ultimate period. And there's also this A thing. You take half of that A thing and the time at the peak and the time when half the A thing crosses the curve, and you find this B thing that's related to this whole thing called F, which is related to omega, and omega is related to period ultimate, and dead time is related to C, which is C is related to F that I discussed, and then you get this whole thing, and you try to find your parameters based on that. I used an Excel solver because it seemed easiest. I did not want to try to mathematically solve something with arctangent in it because it's been a long time since I've had to do that. And so here's an example result for the relay thing that I did. When you first turn it on, you get a period of transients here. We assumed that the period of transients was about 6 times the time constant, and we used a given time constant as a starting point because we didn't actually have any system parameters up until this point. And then after that, I would try to get about at least 3 curves after the transients, 3 nice curvy things here. And I'm going to zoom in on those curvy things here for a minute. That just takes out the transients, that's all I did. So you can see more of my nice 3 curves and the output in liters per minute, which is a gas flow, the input in percent, and this is over a course of 30 seconds, which is nice. And after I plotted this, I could have just analyzed it and gotten the parameters, but there was a voice that told me I needed to do more. A voice that many of you may be familiar with. And this voice was oddly specific, and this voice said, why don't you make the relay input wider? And so I did, and it changed things slightly. And so I attempted as best as I could to match these two graphs to show what happens when you make it wider. And, oops. Sorry, having a moment. Okay. All right, so when you make it wider, not a whole lot really changed when I made it wider. When I made the input wider, and not a whole lot changed at all really. The amplitude increased slightly, and the period went down, or increased slightly, but not a whole lot changed. And then the voice said, make your input narrower than your original input, and a lot changed. Suddenly the periods were smaller, and I got more waves, and my amplitude went down a lot. And then the voice said, do something else. It said, take your floor, which is the bottom one, and push it towards your base, which is the set point, and make your ceiling high. And you get this. And I want to discuss these further in just a second. I'm just showing you right now. And then the voice said one final thing. Take your ceiling, push it towards your base, and then take your floor, which is the F, and make it lower. And what did I learn from all this? I got a bunch of different system parameters, and I kind of averaged them all together. But what did this really result in? And I'm not entirely certain, but just judging by looking at things, it seems that anytime I lower the ceiling, the period gets smaller and the amplitude also gets smaller. Like I said, this is all on the same scale. Like it's all 5 to 50 and 2 to 16 on both sides, so there's no visual trickery going on here. When you lower the ceiling, it appears that the period gets smaller and your amplitude gets smaller. However, when you change the floor, I didn't see a whole lot of variation consistently when you push the floor down and all of that. So I'm done discussing that now. Thank you. Some conclusions based on the parameters that we got during the second half of our experimentation. This shows our ultimate controller gain for the 3 different regions. I am the lower region, so that would be the alternate method. The other two are the standard method that everyone else did. And as we went through different areas of the control system, the ultimate controller gain seems to increase kind of, and the regular system gain seems to decrease kind of. That's interesting. And we get a similar kind of thing with the dead time and the time constant. As dead time goes down, so does the time constant apparently, except for that anomaly there on the left. I can't explain that. That just seems to be what our system does. And thank you very much.